Alright, hello and welcome. So here we are. Our next question is magical string, LeetCode, so medium. Let's jump right into it, I think. Let's not waste any more time here. So I haven't looked at this problem yet, so this will be, so in theory the other questions were supposed to be pretty quick, but there were kind of a lot of things I wanted to think about and look at. But this is going to be, well, we'll see. Let's see how this goes. So a magical string S consists of only 1 and 2 and obeys the following rules. So there's only characters 1 and characters. Ooh, there's a lot of downvotes. Ooh, that's a lot of downvotes. Oh boy. Uh-oh. We might not be getting this one today. We'll spend a little bit of time on it. I don't want to waste a lot of time. String S is magical because concatenating the number of contiguous occurrences of characters 1 and 2 generates the string S itself. First few elements of S is S equals 1, 2, 2, 1, 1, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2. Oh boy. If we group the consecutive 1s and 2s in S, it will be 1, 2, 2, 1, 1, 2, 1, 2, 2, 1, 2, 2, 1, 1, 2, 1, 1, 2, 2. And the occurrence of 1s or 2s in each group are 1, 2, 2, 1, 1, 2, 1, 2, 2, 1, 2, 2, dot, dot, dot. You can see that the occurrence sequence is S itself. Oh, okay. Interesting. It's magical. This magical string consists of 1 and 2 and obeys the following rules. Concatenating the number of contiguous occurrences of characters generates the string S itself. Okay, that's really interesting. So 1, 2, 2, 1, 1, 2, you get 1 occurrence of 1, 2 occurrences of 2s, 2 occurrence of 1s, 1 occurrence of 2s. Okay, so basically you alternate between the number of occurrences of each of these things. That's really interesting. That's a very interesting problem, interesting question. It's 1s and 2s. So 2 can become a 1 by there only being 1, 2. 2 can also map to a 2 by there being 2 2s. A 1 can only map to a 1 by being only 1 1, and a 1 can map to a 2 by being 2 2 1s. But you can never have more than 2 2s or more than 2 1s that are consecutive, because if you did that, then you'd have a 3, and you only have characters 1 and 2. Oh, this is a super interesting question. Wow, okay. Give an integer n, return the number of 1s in the first n number in the magical string S. The number of 1s in the first n number in given an integer n, return the number of 1s in the first n number in the magical string S. Okay, I don't really understand what that means. The first 6 elements of magical string S is 1, 2, 2, 1, 1. Okay, what? Come on, guys. 1, 2, 3, 4, 5? 5? 5? 1, 2, 3, 4, 5, 6. 6. Right, when it is 6. When 6 elements. Okay. And the first n numbers in the magical string S. Okay. That's super interesting. Whoa. So this number basically goes on infinitely, I guess. I'm assuming. It's this sequence. 1, 2, 2, 1, 1, 2. 1, 2, 2, 1, 2, 2, 1. I'm trying to basically figure out how to get the string to loop. Like there's got to be some loop that happens in the string, and then you can use modular arithmetic to find the answer. N is 1. There's only one value 1. Constraints. N is between 1 and 10 to the 5th, 100,000. So I mean, you could I guess calculate this in linear time maybe. But I think you do constant time too, so you got a lot of downvotes. Oh, it's fun. I have to kind of study the properties of this a little bit longer to really get it. So you have 1 shows up once, 2 shows up twice. So this goes to 1, 2. order to get 2, you gotta have 1, 1. So you have 2. Or to have 1, you gotta have 1. And that can't be 2, so it's gotta be 1. And then in order to have the next one, it has to be a 2. Okay. But this has to be a 1. Oh. How do you generate this string? 1, 2, 2, 1, 1, 2. 1, 2, 2, 1, 1, 2. Okay. 1, 2, 2, 1, 1, 2. Yeah, so 1, 2, 2, 2, 1, 1, 2, 2, 1. And then this has to be a 1 again, right? Because it's the same sequence. So, oh, it's an interesting question, man. Oh boy, it's a bit of a mind bender, huh? Yeah, you gotta really think about this one. So 1 shows up once, 2s show up twice, 1s show up twice, 2 shows up once. You can't use another 2, so it's got to be a 1 because you have to have another 1, right? So you have to have a 1 there. And then in order to have a 2 here, you need to have 2 1s here. But we know this is a 1 because the thing up there is a 1. And we know that this is a 1 because the thing up there is a 1, which is not correct. Wait a second. Okay, how do we generate? Can we generate this string? We know the first value, if it's a 2, then we have to have 2 2s following in order for this value to be a 2. But in order for the second value to be a 2, there needs to be 2 more 1s following, which there can be, but then there has to be 1 1 that follows, which has to be a 1 here, and there has to be a 1 here as well. This can't be a 1, so you have to have 2 2, right? This has to be a 1, and this has to be a 1, which means that this following value has to be a 2, and the value after that has to be a 1. Is this possible, right? So we have 2 2 1 is this 2, and then this one has to be a 1 because if it's a 2 here, then that makes this 2. This has to be a 1. But then if you have a this has to be a 2 then, which follows, right, because this is 2. So since this is a 2, that means this 1, 2, 3, 4, this has to be 2 values. It can't be 2, it has to be two 2s, right? And so then, so 2 2s, 2 1s, 1 2, 1 1. We have 2 2s. This value 1 has to be a 1, right? Because it has to match. And so this 2 matches what? I guess it just repeats again, right? So this, in order for this 2 to be here, you'd have 2 values. They can't be 1s because we started with 1, so we have to have 2s. And then now you have the same deal again. Just repeats. 1 1 2 1. So the string could actually, it's not unique, this magical string. So if we start with a 1, it's the same sequence, actually. Exact same sequence, it has to be. But you could start with a 1 also, or not, but it's got to be the same sequence over and over. So it's actually, this is the repeating block. excuse me. This is the repeating block. And this is just like sort of an entry point, I guess. But yeah, this is what repeats over and over, right? Get this 2, 2 again, and then you have to have a 1. So in order to have a 2 here, you need to have 2 2s. So there has to be a 2, 2 2s, and then and then these are the same, so it has to be 2 here also, which means you need to have 2 1s, can't have 2 2s, and then you have to have a 1 here, which means the next thing has to be a 2, can't be a 1, otherwise you have 3, so you have a 1, so it has to be a 2, but then this is also a 1, which means this has to be a 1, because if it's a 2, then that's a 2, so it has to be a 1, and then we know this is a 2 because we just wrote it, and we know, which means that this is that means that this has 2 things, which has to be opposite, 2 2s. And we said this has to be a 1, which it is. It has to be a 1. Oh no, it doesn't keep repeating, I'm sorry. Wait. What happened? Hold on, no, I'm wrong. 2 2 1 1 2 1. So 2 2 2s. This has to be 2 to match. That means you have 2 1s. This has to be a 1, and this has to be a 2. And then, which means, oh no, I'm sorry. This has to be a 2. No. This has to be a 1 to match. No. Yeah. It has to be a 1 to match, so this has to be a 2. And then, this is a tough one, man. This is kind of hard to follow. So if you start with 2, you have to have 2 2s, otherwise you can't. You have the matching 2 means this has 2 2s, and then another matching 2 means there's 2 1s, and then another matching 1 means this is a 2, another matching 1 means this has to be a 1. A matching 2, a matching 2 means that you have to have 2 2s. A matching 1 means you have to have a 1. A matching 2 means you have to have 2 more things that can't be 1s. A matching 2, excuse me, another 2 means you have to have 2 1s. A 1 means you have to have a 2. A 2 means you have to have 2 1s. Another 2 means you have to have 2 2s. Another 1 means you have to have a 1. Another 1 means you have to have a 2. Another 2 means you have to have 2 1s. Another 1 means you have to have a 2. Another 1 means you have to have a 1. Another 2 means you have to have 2 2s. So I guess there is an algorithm for generating this string, at least, a linear time algorithm. The 1 doesn't really matter in front, I think. It doesn't really, it matters, but doesn't matter. It just means that you start with a 1. So this 1 forces you to have a 1, and then you have to have a 2, because you can't have a 1 next to a 1 and have a 1 there like that. Because if you have another 1, that means that this first one can't be. So a 1 means the next digit is going to be different. That's kind of what that comes down to. Next generated digit. And a 2 means you've got to have a block of 2 of the next, and it has to be a different digit. Every next digit has to be different. Alternate. But the question is there a pattern, right? Doesn't look like it. It doesn't look like it. So there's 2 2 1 1 2 1, 2 2 1 2 2 1. So there's 2 2 1 2 1, and then there's 2 2 1 2 2 1. And then it's kind of interesting. You have totally different 1 2 1 1, 2 2 1, not red. Green, I guess. 2 2 1 2 1 1. I don't see a sequence repeating here. I see 2 2 1 1. I see 2 2 1 2. I see 2 2 1 2. Excuse me, but this 2 2 1 1 then follows with a 2. And so it's different. And then this 2 2 1 2 2 is different. Yeah, I'm trying to see if there's like a starting with 2 2 2 2 into something that repeats, or maybe 1 1 2 1. We see 1 1 2 1 here, and 1 1 2 1 here, but this is followed by a 2, and this is followed by a 1. But here we see 1 1 2 1 2 2. So maybe things are repeating at this point. Let's see, what do we get if we continue this? So we have this part here. If we keep going, we just kind of say this goes here, and this goes here. So now, yeah, sort of, this whole piece is over here now. So we have to have a 2 here because we got a match. And this 2 matches these 2 2s, these 2 2s. Oh no, I'm sorry. It actually matches these 2 2s. This 2 is connected to these 2 2s. So now we match this 2. We have to have 1 1. We match this 1. Need to have a 2. We match this 2. Need to have a 1 1. Match this 1. We need to have a 2. Match this 1. We have a 1. Match this 2. We have a 2 2. Match this 1. We have a 1. Match this 2. We have a 2 2. Match this 2. We have a 1 1. We kind of keep going this way. Match this 1. We have a 2. Interesting string, you know. It's equal to itself. It's equal to its occurrence string. Yeah, it's really interesting. It's a really interesting, which means you only have to do this once. I think the string is infinitely long. That's the thing. So I think you need to have an algorithm to generate the string and count the ones as you generate it. I think that's the trick. I think that's the trick. I don't think it's actually I don't think it's actually a like feasible thing to I don't think it's a feasible thing to try to write a routine that generates this, and not a routine that generates this, but something that finds the repeating part and then can calculate the answer directly from the repeating portion. I don't think this repeats that way. So we were saying this 1 1 2 1 maybe repeats. There's a 1 1 2 1 1. Let's use the purple one, or let's use this one. 1 1 2 1 2 2 1. 1 1 2 1 2 2 1. But this one becomes a 2. Yeah, the thing about this string is it could be infinitely long, this magical string. So maybe we're better off just calculating it directly. I think this is a relatively easy question if you don't try to calculate it the infinite version. I think it's okay. But yeah, we kind of need something of a data structure to hold the characters that we... It's sort of like a queue, I guess. Yeah, let's use a queue. Let's try to use a queue. And we're going to have q, q. We'll use integers, q. We're going to say q dot push a 1. And then there's q dot pop left. We're going to say int which equals q dot front pop left, and we're going to say if which equals 1. Then we're going to increment our count. So we're basically going to write like an automation of this plus plus ret. There's only 2 options for what could be in the front, so we really don't need ints. We can do booleans. We can just do 0s and 1s. And we push a 0. 0 will be a 1 and a false, and then the other one will be true. So we do not which. Pop left. So if we have not which, then it's a 1, and we're going to say we have it's two queues that we look to. So there's Q1 and Q2. Well, the deal is Q1, we copy from Q, right? And we evaluate, and we actually move to the next. So we actually pop it. Yeah, we do actually pop from the left. So we're going to say while Q and we actually have a processed Q, and it's really just processed because we think this is infinite, right? So we can do both. While the queue is not empty and our processed is less than or equal to n, yeah, we do want to actually process the n elements. Right, this is annoying because it's one element, right? Should be less than or equal to n. Actually, it's less than it because we're starting off at 0, right? So if we process the 0th index, n is 1. Yeah, it should be less than n. So we also it's taking a while, huh? Yeah, 20 minutes, not too bad. Okay, so Q is not empty, and we haven't processed all the parts of the string yet. This actually should be a for loop, believe it or not. Yeah, just making a for loop. It's really just a for loop. Yeah, because we peel a character off each time. So queued up front, pop left. If it's not which, we're going to increment ret, and we're going to say int rightmost equals queued up back. Can we do that? Queued up back. And we're going to do, so if it's a 1, that means we're going to push into the queue the opposite value 1 time. The opposite of which? It's actually the opposite of the rightmost. It's Boolean. If it's a 2 that we just popped, then we're going to push onto the back. And we do this every time. We do this for no matter what the, excuse me. No matter what, we want to see what's on the right side. We're going to push twice the opposite. Yeah. If it's a 2, then we push 2 of the opposite thing. And it has to be 2 of the opposite thing, because if it's the same thing, you push 2, you're at 3. So it has to be the opposite thing every time. We're going to do the negation. We're going to say rightmost, or toggled, or new vals, let's just say. Okay. The problem with this is I don't think you can see the back in a queue. I might have to use a double-ended queue. Oh, you can. Okay. All right. What does this look like? Okay, apparently we don't have pop left. First element, pop. Okay. Wrong answer. Nice. What? Really? 1, 2, 3, 4, 5, 6. Should be 3. Why did I get 4? So we have 1, right? So initially we have a 1. Say which front, pop the 1. So look at the back, it's a 1. Not 1 is 2. We say it's a 0, which means process this. So we increment, we push the 2, increment 1, and then we have 2, so new value is going to be 1. So okay, now here's the tricky thing. We see a 2, which is actually going to be true, but we see a 2. The problem is it actually depends on what the not back is. there's only one we push 1. If we see a 1, wrong. Actually, for the first value needs to be not counted. When we see a 1 in the front of the queue, we write 1 down, and we have to add, the next thing has to be not 1, so it has to be 2, and we need to have 2 of those. Oh, see, that's kind of awkward, huh? See a 1, we write 1. Does match, basically. The only reason we write 2 is because it's not 1. So now we see 2 somehow. We write 2. That means, so since we have to write a 2, we have to write 2 2s. Save a 2. That counts for those 2s. We see another 2. Write that 2. That gives us 2 1s. We see a 1. We write that 1. That gives us a 2. We see another 1. We write that 1. That gives us a 1. We see the 2 now. We write the 2. That gives us 2 2s. But the first one that we write actually is kind of interesting. We write the 1, and then we write a 2. We read the 2, we write the 2, but the thing that we're writing, we need to put, if it's 2, we need to put 2 of them. If it's a 1, we have to put 1 of them. So what we're writing actually matters a lot. So it actually depends on the new value. So if the new value is, okay, let's do it this way. All right, if it's just one value we read, then we increment. But in any case, actually, it really just matters what we're going to push. Really just, yeah, okay. So really, if it's not which, we increment ret. Just to say ret plus equals int of not which. So no matter what we do that, and then we say if new val, if rightmost so it actually doesn't matter what which is, because we're always going to do the opposite of whatever the rightmost value is. It's always going to be different, right? Because if we add a 1, like we see 1 and 1, they match. The opposite is 2. So you have to add 2 of those 2s. And then we pop a 2, and that covers those 2. This is so confusing. So confusing. Why do we add 2 2s to the queue? The reason we add 2 2s is, I'm sorry. The reason we add 2 2s is because there's 2 of them. If it's a 2, there's got to be 2 of them. If it's a 1, it's got to be if the opposite value, so if the opposite value, if it's a 0, meaning it's a 1, we only need to push one of these. Otherwise, we push 2. And we put the opposite. Like, this is always the case, I think, that you must push either you push 1 of the opposite thing or you push 2 of the opposite thing. And the amount, what the opposite thing is what you push. So so you pop 1, you see 1, you pop 1, you transcribe 1, and now you need to push a 2. I need to push 2 2s because you're going to transcribe that 2. So now you have these 2 2s. You pop that 2, it means you transcribe it. That's actually already accounted for now, which is weird. I think I'm doing this wrong. I actually think I'm doing this wrong. Yeah, you actually would skip that first 2, I think. You transcribe another 2, and that handles the next. Yeah, this is really confusing. I think the initial state needs to have, I don't know, man, this is making my head hurt. You need to have the first, the thing that you transcribe you want to pop. And then you say, if that's already accounted for, if it's already accounted for, which it is initially, then you want to take the opposite thing, and if it's a 2, you have to write 2 of them. But then that first 2 is accounted for, right? So you actually just pop that one immediately. So really you would pop left, right, because that 2 is accounted for. You take the next 2, and you'd increment 2, actually. You would plus I. When you pop left there. So you have a 1, you write a 2, you push 2 2s, you pop the first 2 because you would transcribe that, pop it, already count, increment I, see the next 2, that has to be 2 1s, so you push 2 1s, and you pop a 1. This is so confusing. This is so confusing. What's the algorithm? I don't get it. I don't know. Seems to make sense in my mind. You start with a 1, transcribe the 1, realize that in order to continue you need to write a 2, so you transcribe the 2, but then you need to pop another 2 for that 2, but that means you transcribe a 2 here, which means you need 1s here, but then you transcribe a 1 and realize that you need a 2 over here, and you have to transcribe another 1, which means you need another I don't really know how this works algorithmically. It has something to do with a Q, but another 1 means you need a 1, you transcribe a 2, so you pop a 2, and then you say, okay, that means I add 2 2s to the Q, you pop a 1, and that means you add a 1 to the queue, and you pop the 2, and it means you add 2 2s, and then you pop another 2, means you add 2 1s, pop another 1, means you add a 2, oops. Pop a 2, means you add 2 1s. I think this is fine. I think this works okay. It's just, so you put 1 in the queue, pop 1, and say, no. So, okay, I think this is the part that's confusing. The initial part seems kind of weird, but the part after that is fine. So when you have a 1, popping it means you transcribe it down here, and you realize you need the opposite. You need a 2. So you push a 2. And then you transcribe a 2, you pop it. And, okay, I think you just pop. But when you push 2, it doesn't matter what you push, actually. You just push one of the opposite. So if you see, yeah, this is very confusing, but so confusing. It's really confusing. You see a 1, you transcribe the 1, you pop the 1, and then you add the opposite of that. So you say if it's a 1, so if it's a 1, you're going to push on the back the opposite. And how many of those are you going to push? Well, I think you only push 1 if it's a 1. Right? Now, that's not necessarily the case. Let's only push 1 value at a time if we don't know that we need to push more than 1 value. Because you can push 2 2s. It just so happens that it's 2 2s. But it could be a 1 that goes here. You don't necessarily know what comes after this. So we'll just put 1 at a time. But here when you pop the 2, you realize you need another 2. See, that's the thing that's kind of tricky. It's actually, you don't do the opposite of the 2. You do, yeah. So if it's a 1, then you don't necessarily, yeah, see, that's the thing, is you don't necessarily need to, like, there's a few different rules that figure out which one's which. So you start off with a 1, pop a 1, transcribe a 1. You can't put another 1 here, because if you do, that means this has to be a 2. So anytime you see a 1, the next thing has to be a 2. Is that true? No, it's not always the case. It's not always the case that the next thing you push is a 2. It's probably a 2. If we've matched up to that point, then the next thing always has to be the opposite. Even if it's a one or 2 things, it always has to be the opposite. So we're always going to push at least one of the opposite. Yeah. So now we're matched up to this 1. So we're actually matched here. So that's significant. I think that's kind of the tricky thing, is that, like, we're not always matched. Like when we get the 2 here and we transcribe the 2, we're actually not matched. We need to add another 2 before popping. So yeah, see, that's the thing. If there's a 1, if we just pop a 1, then we're fine with sort of adding just one element. But if we just pop the 2, then we may need to add to the back. Oh, dude, this is so much harder than I thought it was going to be. Why is it so hard? I thought this was like really straightforward, but it's not. It's not straightforward at all. It's actually really challenging. What's going on? Why is it so hard? I'm considering like just writing a whole bunch of different rules to do this. A part of me is trying to make it really simple, and it's making it a lot harder. Like usually simplifying things makes things easier, but in this case it just seems to be really complicated. So yeah, the rules I think aren't that simple. So the logic's not that simple to generate the string. So when you see a 2, obviously you pop the 2 and you transcribe the 2, and we're not totally matching the string because this is supposed to have 2 elements, and this previous element was a 2. So we actually need to add another 2. But would you always add 2 2s here? I don't think so. Not necessarily. So you don't necessarily know if you should add 2 2s there or not. But here we happen to know that we should add 2 2s. Okay, so there's like some kind of a rule that figures that out, but I really don't actually know what that should be. I think it's just because we popped this 2 now. I want to say that if we push a 2, we should push 2 2s. Not necessarily. Because now we pop this 2. And it's already taking account, it's already accounted for. I don't know, man. I'm wondering if I should just start the string with like a few characters, the queue with a few things. So we just started with like 1 2 2, right? And now this 2 matches this 2. When you look at this 2, it's got to be 1 1. Then you pop 1, and it's got to you have to have a 2 here. And then you pop another 1, it has to be a 1 here. And you pop a 2, and it has to be 2 2. You pop a 1, and it has to be a 1. Because it has to be the opposite. And then you pop a 2, and it has to be 2 2. 2 of the opposite. Pop a 2, it has to be 2 of the opposite. Again, 2 1s. Pop a 1, has to be 1 of the opposite. Pop a 2 has to be 2 of the opposite. Right, and this is the only way this could work after that. So I think actually you just fill this queue with like 3 things first. I think that's what you do. You just push false true true in there, and then it makes sense after that. I think that's what we have to do, because otherwise it's too confusing. Yeah. And right, so we'll front rightmost, and we'll say pop, and we'll say if it's a false, we're going to increment ret. Excuse me, and so actually, false true true. What's n? If n is less than or equal to, if n is less than or equal to 3, turn 1. Excuse me, we'll set process to equal to 1. And we're actually going to we're going to pop oh boy, I don't need this process here. This is very interesting. So okay, we actually are going to start with I equals 0. We're going to count the first element and the second element, right? We already look at 1, we match 1 and 1, we match 2 and 2. Things only get interesting when the queue already has a 2 in it. One, 2, 2, I think is where things get interesting, right? So we say there's 1, 1, there's 1, 2, 1, 2, 1, 2, 2, 1, 2, 2, right? So what happens, we get 1, take a look at 1, we want the opposite, has to be because we put another 1 that will contradict that 1, so it has to be a 2. Then, because that's a 2, we transcribe this 2, but that means there has to be 2 2s. And then we transcribe this 2, we realize there needs to be 2 1s. Okay, I think this is where things get interesting. I think it's actually only this 2, because when you see this 2, we pop it and we push 2 1s. And then from there on, the rule is the same. We pop a 1, push a 2, pop a 1, push a 1, pop a 2, push 2 2, pop a 1, push 1. The opposite of the back. It's just the opposite of the back, and then if it's 2, then we have to push 2 of those, right? If it's a 1, then we push 1, and that's how it is for the rest of the way. It's only the first one where you have an issue. Now the question is, if this ever repeats anywhere, which I don't think it does. I think you can prove that it doesn't repeat. But if it ever repeats, then we have a problem. Then we have a problem, but I don't think it does. I don't think it can. I think it just goes on forever. But yeah, you only really have an issue in the beginning. You need to get this 1. You basically 1 2. You skip 1 2. Set ret to 1. And then you have just 2. 2, so you push true, right? And that just keeps things simple. So let's do it this way. Just say push true. Start off at 0 1 2. So 2 is the element we're going to start at, which is true 2 in the queue. And when you read this 2, these 2 are accounted for. It's actually this 2 that you pop, that you add the 2 1s, right? Okay. And so pop, you say if it's a 0 that you just looked at, or a 1, then you're going to push 1 of these. Right, you see a 1, you're going to push 1 of the opposite. You see a 2, you're going to push 2 of the opposite. Whoops. And when you see 1s, you increment by 1. When you see 2s, you don't. And that's it. Yeah, I is 2. N is 3, 0 1 2. So if n is 3, you would do 0 1 2, and you would stop. But when n is 4, so okay, how do we do now? Okay, a little bit better. 50,000. 10 to the 5th is 100,000. This is a lot. Okay, I think we got it. This was frustrating. I'll give this a problem a like. If we got it correct, I think we'll give it a like. But oh, look at these numbers. Oh, they're like just slightly off of half. Oh, that's interesting. It's really close to half. It's like just a few numbers away from half each time. That's super interesting. I'm just thinking there's got to, like, just in case there's something I missed, something I did wrong. But yeah, I think we got it. Let's give it a shot. I'm thinking maybe there's somewhere there's an error that I made. No, we got it. Okay. Interesting. Looks like there is some kind of a pattern though. let's see, let's do, we can actually run this locally, right? How long did we spend on this? We spent a lot of time. This, I think this is fine. Just run it again. I think this is fine. It's just, okay, well, let's do this. Let's do one less operation. Well, actually, the optimizer probably the optimal. What do you call it? The yeah, I guess the optimizer. The optimizations probably would. Compiler probably optimized this code a little bit. That'll make it slightly faster. Oh, there we go. Okay, 12 milliseconds. I made it a lot faster. 1, 2, 3, 4, 5, 6. Yeah, I made it like twice as fast. You really don't need to do this check, do you? It's always not empty. Could do the negation here also. You could, instead of negating this, you could just swap these. Just looking for different optimizations you can do. Really don't need this to have its own value either. This could just be right in there. Actually, no, you do need to in order to pop it. This could be popped at the end. I think. Which means you don't need this variable. And gonna push one value no matter what you do. Right? Seeing if there's anything I could do to optimize this slightly. Okay. So new value. Q back. You're gonna push. That's pretty much it. I don't know if you could do better than that. Maybe there's something else that you could do I'm missing. But I think the people who made this even faster, they probably found, what I'm thinking is if you run through a few different test cases. LeetCode. Let's do, what is this? Look at this problem. Excuse me, magical string. Okay, this is your solution. Okay, what we want to do is call our solution. And for, say, int I equals 0 or I equals 1 to I is less than or equal to 100,000. We want to call s.magical string of I, and we want to print it. Oh. Alrighty, so basically we're looking for patterns. That's the idea. It's got a ways to go though. Wait a second, it's 12,000. Yeah, okay. What am I missing here? Hold on. We want to print out a little bit more information. I'm going to say I. I'll lower my voice too, people are sleeping now. I. And result. What I'm thinking is that there's probably a pattern. I think the pattern is not too hard to see, not too hard to find. Oops. Oh. Okay. Whoa. It's going quickly. Oh, cool. Okay. So I already went through 20,000. Wondering, it's very close to half. That's the thing that I'm kind of noticing. It's like just a few amount, there's just some amount difference between a half. Also wondering if there's a way I can save this somewhere, you know? Maybe we could do this. Let's do this. Also, you guys are really, it's a little bit easier on the eyes here. Okay, let's do I, result, standards, yeah, and we're gonna do, say diff from half. We're gonna say I divided equals 2 minus result. Just as it is. And let's do this. Oh, okay. Ah, I forgot. This is a comment. Python. Python uses a double / for an integer division, whereas C++ uses double / for a comment. Python uses a different symbol for the comments. So, see how long this takes. This should take a few seconds. This should take some time. This is writing a lot. You actually can, there's a lot of, I guess, sort of back and forth going on here, like writing one line at a time to the log, I guess, is kind of expensive, I suppose. Like there's just a lot of buffering going on here. I want to say something like that. Basically, you want to do your writes and reads, I think, to the buffer, probably in like chunks, something like that. Otherwise, I think this would take a while. That's what it seems to be doing. It seems to be taking a while. I'm wondering if there's like optimizations we can run in here, maybe. Okay, let's do, yeah, let's try that. Let's say, I think 03 is the highest optimization level. Oh, that's fast. Okay, okay. All right. I didn't really check to see how long it took. I think it's a lot faster though. We hit like 15,000 in like a few seconds. So we'll see how long this takes. It's definitely taking a while though. Alright, I was not expecting this to take this much time. Okay, how far did we get? Waiting a few minutes. Oh, we got pretty close. 80,000? It's only supposed to be 100,000, so okay. Let's do this. I wonder if you can do something like this. And then at the end you can now this might be like overflow the memory or something, but let's see how this goes. I'm very curious about this one. I don't know if this will even compile. Okay, what do we have here? Oh, it's going. It's going. Alrighty. So maybe we'll... Does it crash? I wonder if it crashes. Let's do it this way. Let's just let it sit for a while. Alright, so basically, I think there's some kind of a pattern here, but yeah, getting all 100,000 executions is definitely a lot. So I think that we don't use that many test cases. I think there's a way. I think there's a way to calculate what this number is supposed to be in a more direct way, and I think that's what the people who got the highest runtime did. I guess we'll just look at one more problem. This is kind of, well, that's all right. We'll stay here. I think basically what we're looking at is like this. Excuse me. This problem. This video, this live stream, which I'm going to stop at some point, and it'll just be like a live stream video on YouTube. Really, this one should pertain kind of only to this problem, right? So I kind of don't want to mess around with like too many other things. Now I realized on just a video earlier today, I kind of did mess around with a lot of different things with C++, but forgive me for that. I kind of had already solved the problem though. That was kind of why I did that. But yeah, let's. In that case, I guess we'll just focus on this. So, I mean, we have to wait like minutes just kind of staring at this though. Yeah, I was gonna say I could look at another problem. Well, yeah, I guess that's fine. Yeah, that's all right. It's fine. Not a big deal. I think it's okay. Let's just grab another problem and look at it while we're running this. This is it's really taking a while though. Now the question is, are we running out of memory at all? Because that's what I think is going to happen. I think the string stream is going to run out of memory. Computer's going to run slowly while we do this. My whole computer seems to be. Oh no. Yeah, it's. I actually want the title, I think. But oh. Oh, I see. Okay. We go to 300. This is lagging. Predict the winner. Okay, we could read this now, I guess. Oh, it's still going. Oh man. Wow. Whoa. We optimized this one, right? No, we didn't. Oh, that's why it's taking so much time. We made a mistake. Completely forgot. I completely forgot. Okay. Should be nothing in it, yeah. Okay. Sorry about that. Yeah, it's gonna be a little. Oh, that was a lot faster. Yeah, there we go. Oh, there's nothing in it. Oh no! Come on. Oh, that's terrible. Yeah, I should have done. I really should have put this at like 100 or something to test that this works the way I think it does. Oh no. Oh boy. That's really silly. Oh man, well. Okay, that's what we want. Yes, that works. Okay, this is what we wanted. Wow, that was really fast. Oh, it's only 100, that's why. Okay, sorry. Duh. Forgive me, I'm a little silly here, I guess. Okay, this should take a while. So give it like 10 minutes or something. 5-10 minutes. What I really should have done was write a program that takes a command line argument, and then I can run the program with like 100,000 as like an input. Do it that way. That would then, yeah, then I'll have to compile the binary once so I can run it. Any number of values, so that way we can get a quick test case and then a long test case, just to make sure the functionality works correctly for a quick one. Okay. Yeah, we have a whole nother problem we're looking at here. Given an integer array nums, two players are playing a game with this array, player 1 and player 2. Player 1 and player 2 take turns, with player 1 starting first. Both players start the game with a score of 0 at each turn. Player takes one of the numbers, either end of the array, num0 or nums.length minus 1, which reduces the size of the array by 1. The player adds the chosen number to their score. Game ends when there are no more elements in the array. Return true if player 1 can win the game. If the scores of both players are equal, then player 1 is still the winner. You should also return true. You assume both players are playing optimally. Okay, well, depending on how big the array is, this shouldn't be that hard. I think you just simulate this. Nums is between 1 and 20. I think you, oh, well, actually, no. I think you could do a depth first search here. I think, if there's 20 numbers, then you have at most, what do you call that, at most 20 moves, and 10 moves for each player. You could probably solve this with, I want to say you could solve this using, I forgot the name of it now, a little bit of game theory. I forget what it's called. It's like gamma or something, I forget. It's not gamma, it's something else, some weird name. It's like, it starts with a G. What's this called? Also, how are we doing? Oh, we're done. Sweet. Oh, nice. Okay, it worked. Cool. Yeah, like this difference from half is like very close most of the time. Just every so often. Excuse me, there's a difference of 1, difference of 2. And then after a while, difference 1, 2, positive. Yeah. It's so close to a half. So close to a half. Yeah. 28, 29, 27. only like just a fraction of the time is it it slowly starts to fall away from a half, but it's very close to a half. It's really close to a half. Pretty interesting. I think we I don't know. We can there's probably some kind of algorithm to figure out, like, those numbers don't seem to have much of a pattern to them though. You know, these are like very -1 0 0 0 4 times 1 0 1 0 0 0 0 1 0 0 0 0 1 -1 0 0 0 -1 0 0 0 -1 0, a whole bunch of -1 0 -1 0 0 0 -1 0 -1 0 0 0 0 -1 0. Doesn't seem to have too much of a pattern. Maybe there's a pattern here. Excuse me, but I don't really see it. At some point you stop having -1s, it seems. And then you start having 1s. There's a -2 in there. Then you have 1s and 2s. And then eventually stop having 1s, and then you stop having 2s. Oh no, still have -1 there at 639. Oh, here we go, we got -2s for a while. It's very close to a half. -3s in here for some time. -4s. So that's interesting. Actually, the negatives seem to increase for some time. It's 1,000, 2,000. Let's go to 3,000, 4,000, 5,000. Oh, now it starts to. Okay. Let's go to 9,000. Oh, suddenly, you don't see him as much. How about 15,000? Oh no. Looks like it repeats. 30,000? Oh, okay. I guess not. 20,000, 18,000. Yeah, somewhere around 15,000, 18,000 seems to just go positive. Yeah, a little over 17,000, 18,000. 19,000 seems to be positive for the most part. What about when you get to 20,000? Oh, still some negative numbers there. It goes really positive around 20,000. At least I thought it did. It looked like that. How about like 50,000? Yeah, I don't know. At some point it just seems to accumulate. I don't know. I wonder if this is related to primes. Something like that. Prime numbers. I think this is special. Somehow. I think this is somehow special. Yeah, I think this is somehow special. The perturbations, the fluctuations, this function. I think it has some kind of a form to it, something it's related to. I think so. Something about this is definitely There's something going on here. Something going on here. Can't really see it, but it's definitely interesting. Let me move this to just call it data. All right. Close that. Okay, we could end this stream here. I think I didn't really see an obvious pattern. This, I think, you're probably gonna want to either like some kind of either dynamic programming or depth first search. There's a game theory thing you could probably apply to this, which might make things a little bit easier. I forgot what it's called though. Ultra weak, strong. Only three levels. That's interesting. This is gonna take me a while to find. Grundy. There we go. Grundy values. That's what I'm looking for. You can use Grundy theorem. That's what I was trying to find. Grundy theorem. Probably can use Grundy theorem from this. That's Grundy. It's such a strange name. Grundy. Yeah. How do you remember that? There's a bunch of properties too for Grundy values. Chess is not a form of a... Wait. Hold on, I gotta find out again. Impartial? Impartial game under normal play. Partial game only on the position, not on which of the players is currently moving, and where the payoffs are symmetric. In other words, the only difference between player 1 and player 2 is that player 1 goes first. Go in chess are non-impartial. Each player can only play or move pieces of their own color. Poker, dice, or dominoes are non-impartial. Rely on a chance. I don't know if this game is impartial. The one that we're looking at here. Impartial means you have the same decisions, but the decisions you have to make are different depending on what the other player does. You can actually solve this directly. This problem, by the way, this program. You can brute force this in reasonable time. 2 raised to the 20th is only 1 million. It's not bad at all. Yeah. I think you just brute force this. Basically, each decision the player can make, it's either the left or the right that they take from the array. Just put the array into a double-ended queue and do a depth first search, I think, over all the possibilities, and pick the one where one of the players wins. Excuse me, if player 1 wins. Although actually they're playing optimally, right? So what is optimal for both players? I wouldn't say depth first search. Maybe you want to do actually going through all the possible game states doesn't necessarily win the game for player 1. Yeah, you have to actually, I mean, you can still do a brute force approach, but you just need to label every state as a winning state or a losing state. Actually, this is a little bit harder than that. Given that you can go through every possibility, that's good. But the problem is if they have the same score, then player 1 wins, sure. What is the optimal strategy for this game is really the question. The optimal strategy seems to be, the thing is, if you make a move on the left side, and your opponent makes a move on the left side, like you can't necessarily guarantee that your opponent does or doesn't get something that you're going for. It's not obvious what the optimal strategy is for a game like this, if there is one at all. I'm just thinking, I mean, you can totally solve the game. In other words, you can look all the way down into the decision tree. Given the full decision tree, it's not obvious what you should do because you don't necessarily know I guess you have sort of 2 options, 2 different trees, and if you can win in either of those trees, then it's possible to win. But it doesn't necessarily mean you're going to win. because the player can pick whatever he wants, the other player can do whatever he wants. In other words, you have to have the player has to play really poorly every time. I think you'd have to be able to win and I want to say greedy algorithm is probably the optimal. And that's not necessarily true because you can have a situation where I want to say this is related to subsets somehow. You're each going to end up with 10 of the 20 elements. The problem you run into is like if you just pick greedy things, you could be in a position where, or they both pick greedy, then you could pick. It could be like 1 and 2 a few times, but then at one point, the 2 that you pick, the thing that comes after it is like a 1,000 or something. So you pick 2 4 times, and then you leave 1,000 for your opponent. So you would want to pick the other elements, and your opponent would pick the other elements until, like, you wouldn't want to give your opponent a very large number. So then you both would each pick things until, I guess, that very large number is surrounded by 2 other numbers. That could happen. That's a case where the greedy algorithm is not optimal. But given that you need to pick something, excuse me. I think you have a winning situation, a winning position, if no matter what your opponent picks, you can, no matter what your opponent does, you would still win. You'd either tie or win. Call that a winning position. And then a losing position would be the sort of opposite for the other player. But positions could be neither winning nor losing in that, there could be some branches where you don't win and some branches where you don't lose. Well, a winning position for player A would be such that all of the positions that player 2 can pick are also winning positions for player A. They're losing positions for player 2, or player B. That makes winning position for A. Well, it's not any. It's yeah. There's some like sort of symmetry where like if you swap the players, there's a winning position for A, losing position for B is a winning position for B is a losing position for A. But I guess the point is, if all of the positions that you can move from If any of the positions that A can move to are winning positions for A, then the position A is in is a winning position for A and a losing position for B. When B moves, any of the positions that B moves into, if any of those are winning positions for B, then B is in a winning position. I.e., if any of those are losing positions for A, then B is in a losing position. Yeah. And a winning position is such that all of the positions that you can move from, your opponent will lose. All the positions that you can move from a move to or winning position, or actually a winning position is if any of the other positions are winning positions that you can move to. The winning position for A would be a losing position for B, and any position that A can move to would be winning positions. Excuse me. A losing position is the opposite of a winning position, so it's a position where all of the there's not any, so all of the positions you can move from are not winning positions, or they're all losing positions. And a losing position for A would be a position where all the positions that A can move to are losing positions, and all of the positions that B might select next are winning positions, or any position that B might pick next would be a winning position for B. Yeah, it gets a little confusing. I think we can use an algorithm like that sort of does like a winning and losing kind of, what do they call that? Sort of winning and losing assessment, or what do they call that? Assignment. You assign winning or losing to all the different states, and just do a depth first search. I think that's fine. It's just player one is going to try to pick a winning position for himself, and then player two, once that's been picked, has the option to try to pick a winning position for himself. So there is sort of a back and forth there. Actually, this game is, I think, decided because, and yeah, I think this works because since the two sums for A and B are either one of three things that are equal, A is greater than equal to B, A is greater than B, A is equal to B, or A is less than B, that means that the game always ends in either a win or a loss, no matter what. So there's no draws in this game, as defined by the rules here, that player one, even if they draw, would be technically winning. So in that case, actually, this game is decided already from the beginning, because there's always going to be a sequence to I mean, that's pretty much it. It's that all the leaves are either win or loss, and so every parent node is either a winning node or a losing node for the player that went before. Either has the option to win or doesn't have the option to win. Which, if it don't have an option to win, that means they lost, and if they do have the option to win, that means they won. Which means that by induction, every parent can always has the option either winning or losing. So there you go. Yeah, that works. That'll work. Pretty interesting. Look at this plus. I think I got this one already. We'll come back to this later, but Yeah, I should end the video here. I don't know why I went on so long here. I guess I got kind of distracted. I wanted to keep thinking about this problem. All right, we'll look at this tomorrow. So yeah, thanks for watching. Appreciate it. Talk to you soon. Interesting question. Yeah, magical string. That's something. I don't know how. I don't know. There's probably a shortcut there somehow, but I don't know it. So that's okay. All right. Take care.